Hi students, as a part of IR spectroscopy, today I am going to discuss with you about the types of vibrations or the fundamental vibrational modes in molecules. Fundamental vibrational modes in molecules. So while explaining the principle involved in infrared spectroscopy, I have clearly explained to you that whenever the IR radiation is irradiated on the molecules, then whatever the bonds which are present inside the molecules vibrates. Whatever the bonds which are present inside the molecules vibrates. Now we are going to discuss that only, that is in how many ways the bonds present in the molecule will vibrate. In how many types the molecules, the bonds present in the molecule vibrates. So we are going to discuss that only, that is types of vibrations. That is in how many ways the bonds which are present in the molecule vibrates whenever the IR radiation is irradiated on the molecule. Irradiated on the molecule. So basically the vibrations can be classified into two types. Vibrations can be classified into two types. The one is stretching vibrations, and the second one is bending vibrations. Stretching vibrations and bending vibrations. Right? So these are the two vibrations which basically occurs inside the molecules, which occurs in between the molecules whenever the IR radiation is irradiated on the molecule. So now let us discuss about stretching first. Stretching vibrations. So these are the vibrations in which bond length changes, whereas bond angle or bond axis remains unchanged. Right? So what are the stretching vibrations? These are the vibrations in which bond length changes, whereas bond angle or bond axis is remain unchanged. So bond length will change, but bond angle or bond axis will remain unchanged. Right. And these particular stretching vibrations can be further classified into two types. The one is symmetric stretching, and the second one is asymmetric stretching. Symmetric stretching and asymmetric stretching. So now listen carefully. Symmetric stretching. What do you mean by symmetric stretching and asymmetric stretching? So if you take the example of CH2, CH2. Now there are two possibilities. So either there will be an increase in this bond length, or this is also possible, increase or decrease of bond length is possible. On the other hand, this combination is also possible. That is, one bond is increasing, that is bond length is increasing, another bond length is decreasing. This is possible. This is also possible. Another case is CH edges. So this bond length can be increased, this bond length can be decreased. So 4 cases with the CH2. Either 2 bond lengths which are there between the carbon and hydrogen increases, or 2 decreases, 1 decrease, another increase, next 1 increase and another decrease. Now let us try to label these structures. Well, let us say that this structure is 1, this structure is the second one, this structure is third one, this structure is fourth. So in the first case, students, what is happening? What is happening? There is an increase in bond length. Let us say that I am the carbon, right? Center of mass, carbon. I am the carbon. These 2 are the hydrogens. These 2 are the hydrogens, right? So both are increasing. Both are increasing. Both are increasing, right? Both are increasing. So that is this one. Both are increasing. Both are increasing, right? So another case is I am the carbon same. Both are decreasing, right? Both are decreasing. Both the bond lengths are decreasing. Both the bond lengths are decreasing. This one. Okay. Both are decreasing. Now, both are increasing at once in the first case. In the second case, both are decreasing at once. So such a vibrations in which the bond length of the 2 is increased at once, and bond length which is decreasing at once are nothing but symmetric stretching. Nothing but symmetric stretching. So this comes under the category of symmetric stretching. In these 2 cases, what is happening? Same carbon, center of mass. So these are the bonds. One is increasing, one is decreasing. Right? One is decreasing, one is increasing. One is decreasing, one is increasing. One is decreasing, another is decreasing. So this is nothing but the asymmetric stretch. This is nothing but so based upon this, we can say that these 2, that is 3 and 4, are asymmetric stretch. Are asymmetric. Asymmetric stretch. Asymmetric stretch. Right? So these 2. So I will discuss about the bending later on. I hope you got this. If both are increasing or if both are decreasing, then symmetric stretching. If one is decreasing, another is increasing. If one is decreasing, another is increasing, then is asymmetric stretching. I hope you got it right. Okay, I will rub this one also. Asymmetric. This is asymmetric. Those are first, second structures are symmetric. First, second structures are symmetric. I hope you understood this, right? All right. Now we have to discuss among the 2, symmetric stretching and asymmetric stretching, which is associated with more energy. Which is associated with more energy, right? So energy of symmetric is more than asymmetric, or asymmetric is more than symmetric. So see here. So same carbon, right? So two hydrogens increasing or decreasing. So for increasing at a time or decreasing at a time, right, it is making me to work less. It is making to me work less. Either to increase, to decrease. It is very easy, right? So it is not taking or grabbing my much energy. Energy is less. If both are increased or both are decreased, it is not consuming my more energy. It is making me to do less work, right? That is symmetric. So whereas in the case of asymmetric, what is happening? One is decreasing, another is increasing. Right? Another is increasing. One is increasing, other is decreasing. One is decreasing, other is increasing. So this asymmetric stretching is making me to do hard work more when compared to symmetric stretching. This is hard when compared to this, right? When compared to this. So based upon this, we can say that the energy of asymmetric stretching is more than symmetric stretching. The energy of asymmetric stretching is more than symmetric stretching. Energy of asymmetric is more than symmetric, right? Is more than symmetric. Energy of symmetric is more than symmetric. Now energy is more. Energy required for the asymmetric stretching is more than symmetric. Now what will be the frequency order? So what we know? Energy is directly proportional to frequency. So since energy is directly proportional to frequency, so definitely what we can say, frequency of asymmetric stretching is more than frequency of symmetric stretching. I hope you are getting right. Because energy is directly proportional to frequency. As energy of asymmetric stretching is more than the energy of symmetric stretching, and as energy is directly proportional to frequency, definitely the frequency of asymmetric stretching is more than the frequency of symmetric stretching. Got it? Right. Now, in order to simplify the things, I will consider one example for you. One example. Let us take the nitro group. Let us take the nitro group. Nitro group. Nitro group. Right? Now, you have to tell me that is just guess which is symmetric stretching and which is asymmetric. So dear students, so based upon the structure, it is very clear that it is symmetric stretching because both are increasing, right? And it is asymmetric stretching because one is decreasing and another one is increasing. What is increasing? What is decreasing? Bond length is increasing and bond length is decreasing. Got it? Now, for the nitro group, I got two wave number values in the IR spectrum. I got one value as 1650 centimeter inverse. One value is 1660 centimeter inverse. Another value as 1550 centimeter inverse. Right. I have taken the nitro group and I have recorded the IR spectrum of it. Now one peak is observed at 1650 Another peak is observed at 1550 centimeter inverse. Now 1650 corresponds to obviously asymmetric stretching, because frequency is directly proportional to energy. So as the energy of the asymmetric stretching, this is asymmetric stretching, students, asymmetric stretching. So since the energy of asymmetric stretching is more, so frequency is more because energy is directly proportional to frequency. So the 1650 value corresponds to asymmetric stretching. 1650 centimeter inverse value corresponds to asymmetric stretching. Right. So 1650 is corresponding to asymmetric stretching. So definitely, obviously, other will be corresponds to symmetric stretching. Symmetric stretching. That is 15 centimeter. 15 centimeter inverse. So this is very easy, students. It's very easy to recognize whether it is symmetric stretching or asymmetric stretching. So now it is very easy. So if there is a nitro group in the molecule, and in the molecule, and you have irradiated the IR radiation on that particular molecule. Now it is giving the two peaks, one at 1650, other is giving at 1550 centimeter inverse. So it is very clear that as the energy associated with asymmetric stretching is more than energy associated with the symmetric stretching, so definitely the energy is, as it is directly proportional to frequency. So definitely the frequency of asymmetric nitro group will be more than the frequency of a symmetric nitro group. I hope you understood this concept. So this is about stretching vibrations. So this is about stretching vibrations. This is about stretching vibrations. This is about stretching vibrations. So do remember that energy required for asymmetric stretching is more than energy required for symmetric stretching, students. Symmetric stretching. And as the energy is directly proportional to frequency of asymmetric molecule is more than frequency of symmetric molecule, or frequency of asymmetric group is more than frequency of symmetric group or atom, whatever it is. So this is about stretching vibrations. This is about stretching vibrations. Now let us see bending vibrations. So bending vibrations. Second one is bending vibrations. So bending vibrations. Now, in which region bending vibrations are seen? In which region of the IR spectrum bending vibrations are seen? Already have discussed. In the fingerprint region, 400 to 1500 centimeters. I hope you understood. I hope you remembered it. Fingerprint region. So these are basically observed in fingerprint region. Now let us take the molecule. Let us take one molecule. Let us say that this group is towards the viewer. This group is away from the viewer. And these two are in the plane. These two are in the plane. These two are in the plane. Any molecule we can take. Right. Now, in this molecule, 4 types of bending vibrations are possible. See here. Okay. 4 types of bending vibrations are possible. One is. So this one, right? So this is one bending vibration. So see, what are bending vibrations? Already I have discussed. these are the vibrations in which bond length will not change, but bond angle or bond axis will change. Bond angle or bond axis will change. Bond angle or bond axis will change. Right. So these are the two groups. So let us take the hydrogens. Let us take the hydrogens. So two hydrogens, let us say that. Now for these two hydrogens, which are these two hydrogens, four types of bending vibrations are possible, right? So one is this. So this is axis, right? This is axis. So bond length is same. So one type of vibration is down, up, down, up, down, up, down, up, down, up, down, up, down. So it is nothing but a twisting, bending vibration. Twisting, bending vibration. This is one type of bending vibration. Twisting. And what is another vibration is possible? See here. Two hydrogens, same. Two hydrogens. So it is like a scissor. It is like a scissor. Right? It is like a scissor. So this is nothing but scissoring, bending vibrations. Scissoring, bending vibrations. This is another type of bending vibration. Next. Like a dog tail, right? So this is wagging, bending vibration, right? Wagging, bending vibration. This is the third type of the bending vibration. Next, this one. Two hydrogens on the same. This is rocking, bending vibration. So this is the first one. Twisting, bending vibration, students, right? Next, scissoring, bending vibration, right? Scissoring, bending vibration. Next, wagging, bending vibration. Next, rocking, bending vibration. So four are possible. Now you have to guess among the four. So I am writing the same molecule. I am not changing the molecule, but I will project or depict the direction. By seeing the direction, you have to guess which bending vibration it is. So let us take the same molecule, C. One is towards, one is away. One is towards, one is away. Any group. So that's the reason I am not specifying the group. One is towards, one is away. Now these are about the hydrogens. Just now I have discussed about the hydrogens. Hydrogen, 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 hydrogen. So this is when bending vibration. This is another bending vibration. This is another bending vibration. Right. Next. So what is this? This is nothing but like this, right? Scissoring. Both are is like this one. Scissoring. Scissoring bending vibration. What is this? Rocking. Rocking bending vibration. What is this? Right? This is what? Wagging. Wagging bending vibration. So what is the last one, student? Twisting. One is below, one is above, one is below, one is above. Twisting. Bending. Right. Now, these four types of bending vibrations can be categorized into two types. Can you guess? One can be categorized as in plane bending vibration. Another two can be categorized as out of plane bending vibrations. So what are these? Scissoring. See, in the scissoring, same plane, same plane. There is no change in the plane. See, scissoring, no change in the plane. So, scissoring bending vibrations and rocking bending vibrations comes under the category of in plane bending vibrations. In plane bending vibrations. In plane bending vibrations. What about this? Wagging. Plane is changed. What is the plane? This is the plane, right? This is the plane. In the previous case, scissoring, same plane, rocking, and scissoring, same plane. But in the wagging, what is happening? The plane has been changed. Twisting, plane has been changed. So, these two bending vibrations are called as out of plane bending vibrations. I hope you got it, students. So these are the four types of the bending vibrations which are possible whenever the IR radiation is irradiated on the molecule. And how many types of stretching vibrations are possible, students? Two types of stretching vibrations are possible. One is symmetric stretching, asymmetric stretching. How many types of bending vibrations are possible? Four types of bending vibration: scissoring, rocking, wagging, twisting. Out of these four, scissoring and rocking bending vibrations comes under the category of in-plane bending vibrations because there is no change in the plane during scissoring or rocking. Whereas in the case of the wagging and twisting, what is happening? There is a change in the plane. So that is the reason they are called as out of plane bending vibrations. I hope you understood this concept. Thanks for watching.